Hi, this is Jani from jDrones. The next video is one of our conference videos that we have been recording in our ArduPilot developer conference during June 2019 at Drone World Congress in Shenzhen. Randy Mackay, he will be talking about the ArduPilot based obstacle avoidance for rovers and boats and others. I hope you enjoy the conference videos.
Our ongoing developments for off-board path planning and onboard path planning. So two different types, two different ways to do object avoidance. Okay? So the first one is our existing solutions, stop and slide. So the way it works is we have a LiDAR, 360 LiDAR spinning around the vehicle. And we build a little fence, a little miniature polygon fence around the vehicle. And then we get the desired velocity from the pilot or the autopilot, and we just make sure that this velocity is short enough that the vehicle does not hit the fence. And we do the same thing for copter and rover. So there's a little function here, very simple, which tells you how fast you can go and not hit the fence. So in rovers, we simply stop. For copters, we can stop or we can slide slightly. So if this velocity hits the fence, we move it a little bit so that it doesn't hit the fence but turns a little bit. For rover, that's a little difficult. So we don't support sliding in rovers. Is that cool? Yeah. So here's an example from many years ago, maybe 2 years ago, of a multicopter with an SF40C 360 LiDAR on the bottom, and I'm flying it. This is my garden. I'm pushing the stick all the way forward as fast as I can. And you can see it stops. So the margin here is about 2 meters. Right? I'm pushing it forward, it does not hit it, because it's building a little fence around the vehicle. Okay, so another solution that we have for rovers is called dodge. So dodging is like this is dodging. So in this solution, we use a LiDAR facing forward, and if we see a LiDAR, the user can set these two parameters: turn angle and turn time. So if it sees an obstacle with the LiDAR, it will turn with this strength for this long. It's very simple method. And with careful tuning of those two parameters, it can work in very specific situations. But it's not a good general purpose solution. So, yeah, it's not a very good solution. For example, if this rock is very long, it may turn back into the rock. So it's not a good general purpose solution. Another solution that we have is called bounce. And this is just for multicopters. And what's good about this method is that it does not require GPS. The way it works is we use a LiDAR and we sense all of these different objects around the vehicle. And then for each object, we calculate a little vector, which tells us how quickly we should move away from that object. So if the object is very close, we move away very quickly. If the object is far away, we move very slowly away. And then we add up all those vectors together, and we come up with one final vector. And maybe that moves you this way. And so then the vehicle leans in that direction. So it works, but the vehicle tends to bounce around like a ping pong ball. So you put it in a room, it'll bounce here and there and everywhere. And that's really inevitable. You can't do much about that if you don't have GPS. That's basically the best you can do. So this is a video from Terabee, which makes a 360 LiDAR, which works with ArduPilot. You can see the pilot is holding the stick up there, the transmitter, and he's not touching it, but the vehicle is moving around here and there and everywhere. So it doesn't hit things, but, you know, it's moving all over. Is that all right? Yeah? Great. So that was what we have. Those things are the solutions that we have. Those are not what we really want next is path planning. And when you think about object avoidance, there are many different meanings. But what people really want is they want to move around the objects. So right now, ArduPilot will stop. Maybe it'll bounce, but it won't move around obstacles until recently. And this is quite tricky. So, for example, if the rover is here and you want to go here, we want to find a new target position that gets us around the obstacle. But it is quite complicated because we have many different flight modes with many different types of control. So now I'm into the next slides are new developments. So the first, basically, for our new solutions, there are two categories. There's onboard solutions and offboard solutions. So offboard solutions are not done on our flight controller. They're not done on the Pixhawk or other ArduPilot flight controller. They're done on a companion computer. Onboard solutions are done on the flight controller. And both methods have their advantages and disadvantages. So first, the offboard solution. The advantage of an offboard solution is we can use a companion computer with lots of memory, lots of CPU, and do a lot of complex calculations. So you can run ROS. Everybody knows ROS, right? So in our ROS setup, you connect a 360-degree LiDAR, like the RP LiDAR, to ROS. Then that 360 LiDAR sends its data into Cartographer, Google Cartographer, and if we can calculate a position estimate in there. Then we can use MavROS to send that position estimate from Cartographer down into ArduPilot's EKF. And then ArduPilot knows where it is and what speed it is. And also for the LiDAR, we can send that LiDAR data also down into ArduPilot. So it comes into the AP proximity library and then into our avoidance library. And then over here, we have ROS's base local planner. And this can calculate a path around obstacles that it sees with the LiDAR. So what we do is down here in ArduPilot, we have our flight mode, like guided mode or auto mode. And the pilot inputs in these modes where he wants to go, or she wants to go. Then we take that position target and we pass it up into ROS, base local planner. And then ROS calculates how to get to that location. And it passes down velocity targets back down into ArduPilot. Is that clear? And then ArduPilot will drive or fly around the obstacle. So here's a video. So here I am creating a mission with Mission Planner. Create 2. And here it's driving. So on the right-hand side is Ross. And you can see it's calculating a little path in green. And then the rover is taking the velocity commands from Ross, and the vehicle drives around the obstacles. Cool? So, it has some problems. And one of the problems you may have noticed is that, let's just look at it again. You see this? It's spinning. This is just a Ross configuration issue. If it doesn't know the path, it can't see the path, it turns around. So we need to fix that. Also, right now, this solution, which is all written up on our wiki, only works in 2D. So in the future, we want to get this working in 3D as well for multicopters. And also, maybe we only want to use this solution in a failsafe. So maybe normally we will fly with ArduPilot's built-in navigation, but if the vehicle gets stuck behind a tree, only at that time maybe we will want to use Ross to help us get around the obstacle. So that's something we also want to do. Yeah. And finally, I just want to mention the downsides of an offboard solution. The problem with an offboard solution is that it doesn't have all the data that we have in ArduPilot. So it doesn't know about fences, doesn't know about stay-out zones. So although you get a very powerful computer to do your complex calculations, the integration is quite difficult. So, onboard solutions. So these are solutions, there's 2 solutions that run on the flight controller. So the Pixoff or the Matex, whatever, it runs on there. We have 2 solutions. One of them is called Bendy Ruler. And this was developed by Andrew Tridgell from Canberra UAV. And the algorithm is like this. Down here is the drone. And it probes ahead of the vehicle by a specific distance. And the user can control that distance, so maybe 30 meters. So it checks first directly towards the target, and then it checks 5 degrees left, and then 5 degrees right, and 10 degrees left, 10 degrees right. And each time it checks, it looks how close does this line get to obstacles. And so it picks the angle which is furthest away from obstacles. And then it also probes again. So it probes again, but this time only in 3 directions. So 0 directly towards the target, and minus 45, and then plus 45. So in the end, it picks the direction where these 2 lines are furthest away from any obstacles. And it also prefers directions that are the same direction as the vehicle is moving. So it chooses the clearest path, but it also chooses the path that is close to its current movement. Okay, great. So let's give a quick video. So this is a simulator test. Here's the vehicle here. and the mission is to go here and then to go here. But there's a fence here. So the vehicle is driving forward, and as soon as it sees this fence, it starts to turn away. Now what's very good about this calculation, about this algorithm, is that it's quite cheap in terms of CPU and memory. And also, it works with dynamic objects. So you can have a mixture of fences and stay-out zones and also objects that are moving around a lot. We've tested this on airplanes with hundreds and hundreds of other birds, clouds, planes, and it can avoid them because the CPU cost is quite low. What's not so good about this algorithm is complex shapes like a maze or a U. In those, if you have a very complex shape, it can get stuck sometimes. Let's see. So here's an example of it getting stuck. So this is a more complex shape, right? It's like a 2. We're trying to get up there to the right. See, it moves around a little bit. Oh, it finally gets through. And here it is coming down. I think this time it gets stuck. Yeah, there it goes. So it can get stuck sometimes. So, yeah, so here's a real test. Sorry, it's a big video. So in this video, it's really quick. Oh, there we go. So it's a very simple mission, just going there and back. It's got a 360 lidar on the top, a Lightwear SF40C. So this is with no obstacles, and it does fine. Then it sees the object and it turns away. Now, it turned away a little too far. We have some parameters to control the margin, so I think we need to make those a little smaller. This is a very recent test. It's just 2 days ago. There it is. So it got around. very new development, so there are still some problems. So here, it gets stuck, unfortunately. It is, you can see it's moving. For some reason, it's trying to decide. It keeps changing its mind about whether to go left or right. Step close to it, and it makes up its mind that right is definitely bad. Then it gets around. Anyway, it's a small issue. I'm sure we can fix it. Okay? So the next one, the next solution that we have is called Dijkstras. Has anybody heard of Dijkstras before? Nobody? Dijkstras? No? Okay. Dijkstras is quite a famous algorithm for finding the shortest path between points. So your car navigation system uses Dijkstras or something similar to find how you should get to your destination. So we have this now in ArduPilot. And the way it works is the very first step is to calculate safe positions, safe nodes. So in this example, we're using the fence, the polygon fence. And the safe positions are these little red dots about 10 meters in from the edge of the fence. And we also include the destination and the origin. And then what we do is we calculate a visibility graph. Visibility graph holds the distances between all of the points, all of the safe nodes. So we need quite a lot of memory to store all of the distances. And then what we do is we set the place where the drone is. We set this location's distance to 0. And then we go to all of the points around the drone, and we set their distance to 0 plus the distance. Right? So this one is maybe 15. This one is maybe 15 meters. So this would be 0 plus 15, so that'd be 15. And this is 0 plus 5, so this one would be 5. 0 plus 4. So we count each one of these nodes now gets a distance. And then we iterate through all the other points, and we say, okay, well this one, has a distance of 5. The distance from here to this here is maybe 10, so it's 5 plus 10 is 15. Okay, but 15 is greater than 4, so we leave this distance at 4. You see? So in this way, we can calculate the distance from the drone to that point. So finally, you do that enough times, and eventually, you get the shortest distance to the destination. And so then we feed these intermediate points into ArduPilot navigation, and the rover will drive the shortest path. Sounds good? Here is a demonstration. This is in the simulator. So you can put in very complex shapes. So you can see it's like a spiral. And bendy ruler would never be able to get through this. And the mission is to go down to the bottom right. Switch it into auto mode, and off it goes. And of course, there's no indecision. There's no, it goes straight along the shortest path. So one nice thing, ArduPilot uses ChibiOS, and which is a very efficient operating system, and ArduPilot is written very efficiently. So even when you have a very complex environment, ArduPilot can do all the calculations for the shortest path very quickly, less than 1/10 of a second. One of the problems with Dijkstras, though, it uses a lot of memory, it uses a lot of CPU, but also it doesn't yet work with dynamic objects. So objects that are moving around. It doesn't work well with those yet. Okay? And we have a few other issues that we're working on. So one of them is, right now, we are reading in data from the 360 LiDAR. We do not build up a 3D map. If an object disappears from view, it's gone. ArduPilot does not remember where it was. So one of the things we want to do is add memory, so that if a 360 LiDAR sees something, we remember where it was. So we're working on that now, Tom and I. Another issue that we're working on is, actually we fixed this one yesterday, but when we build up the little fence around the vehicle, right now that is stored in like a hula hoop, a body frame. So it moves with the vehicle. So we need to store those points in earth frame. So when the vehicle moves around, we remember where that obstacle was. Another limitation that we have right now is we don't back away from objects. So if something comes very close to the rover, it does not back away. So we want to add that too. Also, we have not yet enabled bendy ruler and Dijkstras for copter yet, for multicopters. It works for rovers. It will work for copter, but it's not done yet. Yeah, so here's, sorry, I just want to explain one of the issues again. So we want to add a sensor memory. Sorry, I explained this a minute ago, but I'm just going to explain it again. So right now, our sensor data is stored like a hula hoop around the vehicle. But we want to store these as objects with a latitude and longitude. And actually, we've almost got that done now. Another complication, though, that we're going to have is as we store these objects, how many objects can we store inside of the flight controller? The flight controller does not have a lot of memory. You know, how many points can we store? 500 points? 100 points? We don't know yet. Another thing we want to do is add terrain avoidance. So if you've used ArduPilot, you probably know we already have terrain following. So you can set up a mission like this, where the drone is here, and it wants to fly to the top of that mountain over there. And what ArduPilot will do is it will fly like the red line on the bottom. So it'll, if this is a valley here, it'll fly down into the valley and then back up again to the top of the mountain. But, and that's good, if you are making a map, you know, if you're taking pictures of the valley, this is what you want. But if your purpose is just to get to the other side, just to get to the top of the mountain, what you want to do is you want to take the shortest path. You want to take the shortest path from here to the top of the mountain. So this is more like terrain avoidance. We want to add this in as well. Okay. So, ArduPilot is open source, and we're always looking for new developers. If you want to help us out in this very important area, here's a few ideas. They're split into the two sections, Offboard and Onboard. So if you are a ROS expert and you want to help us, if you could get cartographer working in 3D mode, that would be great. And also for the ROS path planning, we also want to get that working in 3D. So also, there are many different companion computers. Right now, we just support the NVIDIA TX1 and TX2 and the Raspberry Pi. But there are many new companion computers like the Xavier and the Nano. If you want to get it working on one of those, that would be a great help. We don't have, okay, we have something called AP Sync, right? AP Syncs are images that allow people to very quickly get started with companion computer development on Raspberry Pi, TX1 and TX2. We do not have AP Sync images for these other boards. So that's what we need. Okay, for Onboard Solutions, if you want to work on those, help us get rovers and copters backing up. It's actually not that difficult, but an interesting problem. Tom and I did this yesterday, so you can't do that one. And finally is, working on the terrain avoidance that I just talked about in the last slide. Okay, that's it. Thank you very much. These are a couple of the companies that I'm working with and that support me, so I just want to thank them as well. All right, thank you very much.